I'm Shannon Dugan. I'm a sales director with TechStar. And today I would like to talk to you about some flow metering technologies for different process applications so that it will be easier to understand which flow meters will be best for your particular measurements.
Hey, so I'm Joey with TechStar, and we're here in our functional verification unit. So this is where we do a lot of our hands-on training, but today we're going to be using it to show you guys a little bit of installation pointers that we have on the different kinds of flow technologies that we have around. So real excited to have you all here, and let's get started.
Today we'll go over several technologies that are used for flow measurement: differential pressure, positive displacement, variable area or rotometers. We'll go over turbine meters and vortex meters, magnetic flow meters, ultrasonic flow meters, thermal mass meters, and Coriolis meters. For each of them, we will go over the main operating principle, the pros and cons to each, the application fit, and some installation considerations. Differential pressure flow meters use Bernoulli's principle to measure the flow of fluid in a pipe. And there are different primary elements that can be used to make this measurement. So the primary element is what is actually in the line to make the measurements, what's in contact with the process. And the secondary measurement is the transmitter that you use. Also various kinds from different manufacturers. So Bernoulli's principle states that as an increase in the speed or velocity of a fluid increases, then it's inversely proportional to the static pressure. So that means that a pressure drop will occur over a restriction. So if we look at the picture right here, there's an orifice plate, and as the flow increases, there's going to be a decrease in pressure, so a larger pressure drop over that orifice. The pressure on one side and the other side of the orifice is measured, and that is proportional to the square of the flow rate. Your transmitter will then take that information and process it into whatever flow rate that you want. And depending on what kind of transmitter you use, if it's multivariable, you may have live temperature measurements as well. It can give you mass flow, volumetric flow in whatever units that you're looking to measure. Some pros for differential pressure is that it's a very old technology. It's very well used in almost every kind of industry. It's well understood, and it's fairly inexpensive. The problem is that it can have some low turn down. It doesn't have a great range, so you'll just need to be aware of that whenever you're specifying these. And it does have some poor accuracy at low flow rates. It can have very good accuracy in the range that it is sized to measure, and can be used for custody transfer in those ranges. The accuracy does deteriorate with wear. So for instance, if you have an orifice plate, the sharp edges on that can deteriorate because of erosion or corrosion or some sort of wear within the pipe. So that's just an additional maintenance item that needs to be thought of. If you're looking at a venturi or a V-cone or other kinds of primary elements, they have their own maintenance recommendations, making sure that impulse lines are clear, that they're not plugged up, because obviously if you have an impulse line that connects the each side of your pressure to your transmitter, if those get plugged up, then you're not going to get a really good reading either. And if you have a very large change in pressure and temperature, it can also introduce some errors into your measurement, so just be aware of that. Clean fluids or pretty clean fluids are the best application for this. It can measure both gases and liquids, which is a positive to this measurement. And it has a really good range of pipe sizes. So you can do very small lines or very large lines, depending on what your primary element is. And it is very flexible for temperature. Normal temperature ranges, something that would be, something that you can touch without freezing or burning yourself, to very, very hot applications and very cold applications. Differential pressure can do all of that, so it's very flexible.
All right, guys, so now let's talk about differential pressure flow. So there's several different styles of primary elements being the flow body, and then your secondary element is actually your transmitter itself, which will be your differential pressure transmitter. So I'm going to talk a little bit about your, let's say, orifice plate. If I had an orifice plate, I would need to have, for liquid flow, I want to maintain a full pipe like I do on these other ones. And vertical flow is usually preferred. So if I can have 10 pipe diameters upstream and 5 pipe diameters down for liquid, and then if I'm dealing with gas flow, then I want 20 upstream and 10 down. So this particular one here is a Varibar, and those of you that have messed with these before, is this installed right? I'll answer the question. It's actually not. Well, we did that on purpose here. So really what you want on these is you want them installed where the transmitter is below the flow tube when you're in this vertical installation. And the reason of that is it makes it possible for me to get some air bubbles up in here, for air to get entrained in this, and which means I have to bleed the air out every time maybe my system goes down or the pipes go dry. I'll have to sit here and bleed it out. We did this on purpose here in our training center, mainly for training purposes. But this is, like I said, differential pressure. This one is actually a Varibar primary element, secondary element, which is your transmitter itself.
Positive displacement flow meters are really the only flow measurement technology that directly measures the volume of a liquid or a gas that passes through the flow meter. If you take a look at the picture here, there are 3 different kinds of flow meters that are pictured: a piston, a gear, and a helical type. They all work similarly in the fact that they capture a specific volume of fluid and then make it go to the other side of the flow meter so that that specific volume is a certain measured quantity. And then as each gear rotates around or each piston shoves that much fluid or gas through, that's a known quantity. So it directly measures that volume of fluid every single time. The rotating parts actually form the seals, and the more flow, the more the parts rotate, and so the more counts you have, or the faster it's going to rotate around. So that's going to be proportional to flow. If we look at applications where we want to use this, it's good for oils. It's not very sensitive to any kind of pressure or temperature changes or even viscosity changes, so that's a really good. That's really good for that. And it has no straight run requirements. I failed to mention on some of the other ones that with a differential pressure or vortex or turbine, you're going to have a certain amount of straight run in order to obtain a fully developed flow profile. With positive displacement, you don't have to have that. So it makes it very convenient for metering in places that cannot find a way to put in the appropriate amount of straight run. It's really good for small line sizes as well, and you can use it for liquids or gases, but they do need to be fairly clean. The small spaces in between the gears or the pistons have very, very tight tolerances, and anything can clog those up and actually make the meter seize up. So anything that would be in front of the meter in terms of filtration would probably help. So normally in front of a PD meter, you'll see some sort of filter just to extend the life of the meter. These are really good for low flow rates. So sometimes you'll see them in metering some small amounts of oil or small amounts of maybe a liquid into a line, and they're very, very good for low flow rates, which is not necessarily the case for some other technologies. You can also have what's called slippage with PD meters, and that means that because of where there could be liquid or gas that actually slips around that specific volume that you're counting on. So you will actually have a higher flow than what you record. Usually that's because the meter's been in for a while and not maintained. So make sure you follow your manufacturer's recommendations for preventative maintenance for these. And it can also happen if you have a corrosive fluid or something like that, and the metallurgy isn't appropriate for that.
All right, let's talk about a positive displacement flow meters. So in positive displacement, I unfortunately don't have any right here, but let's talk about the horizontal mounting. So we can mount this on a horizontal or vertical. We do want to make sure our flow direction is flowing up. We do need to have, like the other flow meters, we do have to have a full pipe. If we're going to mount it, we do want to make sure that we mount upstream of a control valve. Okay. So straight run requirements on these is we don't need any. So it's just like the Coriolis where you can mount directly to a 90. On a positive displacement, you can do the same thing. We prefer a couple of pounds of back pressure, so we can get 2 to 3 pounds of back pressure, and you may need some filtration. So there are circumstances where we may need to, if we have a little bit of a train solids, we can install a filter in front of it to cut back on any kind of solids getting into it.
The next section we'll talk about is variable area. So these are also commonly known as rotometers. You can have them just as a gauge that you look at physically, and then some of them actually have 40 to 20 milliamp outputs as well, alarms, things like that, depending on what you need to use them for. A lot of times these are found in sample systems because they are easy to read and they come in very, very tiny sizes if need be. So in a rotometer or variable area meter, you have a flow that raises a float inside. The higher the float is raised is proportional to how much flow is going through there. So it's very, very simple measurement because the height of the float is directly proportional to the flow rate that's going through the meter. The other nice thing about this is that the flow rate is linear, unlike a differential pressure meter where you have to do some calculations because the flow is not linear with respect to pressure drop. This one is. So it makes it a very simple measurement, and they are also low cost. These also have no straight run requirements because we're really just looking at the position of float based upon how much flow is going through the line, and they do have a wide range of applications. So they're not really good for liquids that would coat the tube. So anything that would inhibit seeing what's inside the tube, even though there's a float there, and then sometimes there's a gauge, you can usually see the fluid or that's through there. So anything that would inhibit that, so very dark colored fluids, things that are opaque, probably not a great choice for that flow measuring technique. But even if it's slightly translucent, you can use it. These really only go up to about 3 inches. So these are made for small line sizes, sample systems, perhaps measuring, something that's metering into a skid, nitrogen flow in a plant, something like that. Those are really typical applications. The fluids have to be clean, specifically because you have a moving float inside the unit, and if there is anything that could kind of get clogged up in that, the float won't move and your flow meter won't work. They are good for corrosive fluids. You can put gases through them, like I mentioned. nitrogen or natural gas flow that's small, perfectly fine for this. High viscosity fluids, really low flow rates, and small line sizes. Once again, anything that's going to look like it's a sample system or a really small metering skid, these are pretty cost effective to use.
Hey guys, so what we have here is our variable area meters, or rotometer. So here I've actually got two of these stacked on top of each other, so you can kind of see two different styles. On the bottom, I have a rotometer. This is just a dial style meter. Some really important installation considerations is these are dependent on upward flow. So any kind of pump, maybe a gravity pump or something, may not be suitable for this. You do need some velocity to make sure that you need to flow up. You have glass. This is a visual flow indication. So you could have safety considerations. You may have to, if you're dealing with dangerous chemicals, with glass could break or something like that. So keep that stuff in mind. And very, very good technology, been around for a very long time. Basically have a float in here, and you'll see the float movement come up depending on what your flow rate is when they're designed according to the flow rate. But they must be installed in a vertical installation with flow moving up.
Turbine meters use mechanical energy of the fluid in order to make the flow measurement. Inside the pipe, there will be a pinwheel, much like what is pictured on the screen behind me, that will rotate faster as the flow of the fluid goes faster. So if you have low flow, the pinwheel will rotate, but simply not as fast. And usually the pinwheel will have some sort of a magnetic pickup on it, so that every time it rotates, it will have a count. And as the fluid flow increases, the pinwheel will spin faster, there'll be more revolutions per minute, more counts, and then it will transmit to a higher velocity. Some manufacturers will be able to measure bidirectional flow with flow meters. If that's the case, then usually the reverse flow would simply be indicated by a negative number on the transmitter, whereas forward flow would be indicated with a positive reading. Some installation and application pros and cons. These are really good for smaller pipes, moderate cost. You're usually going to have the whole meter, that's the size of the line. So a 2-inch meter is going to be less expensive than a 6-inch meter because you're buying the whole meter body, that's the line size. They do have good turn down, and they can read low flow rates. There is a low flow cutoff for these meters, and so when they are sized for your particular application, it is important to understand what the minimum and maximum flow rates are so that you are able to get the widest range possible out of your flow meter. The cons are that these might have a little more maintenance involved than some other flow technologies. They have moving parts within the line, and they have bearings, and they might wear out. If you have a solution that is corrosive, then you can corrode some of the bearings, and then they would have to be replaced, or just the whole meter replaced. If you have a fluid that can salt up, for instance, a brine or something like that, that can have some wearing effects on the bearings. You can actually salt those up. They can be acid cleaned and put back into service, but usually you don't want to do that more than a couple of times, or you'll see some degradation in the accuracy of your flow measurement just from bearing wear. These are not good for non-lubricating fluids, which means solvents or hot water. They are really good for oils and other things like that. So a lot of times you'll see these in the oil and gas industry. And they are less effective in terms of price for larger pipes. Just as I mentioned, your 6-inch meter is going to be significantly more expensive than a 2-inch meter because you have to buy a meter that's as large as the line size. They can be used for custody transfer, however, and have been for many years, so they can be very accurate.
All right, let's do a little talk on turbine meters. So turbine meters, great technology, been around for a long time. We don't have any here, but a few things about it is on straight run requirements to start off there. So for a straight run, we want 10 to 15 pipe diameters upstream and 5 pipe diameters downstream. You may need more if we have a lot of elbows or valves or control valve, especially. And straightening vanes. So if you do have some valves, you do have some of that, what can actually help, but it's going to be at the cost of a little bit of back pressure or some straightening vanes. So you can install a straightening vane in front of the turbine meter. Filters may also be required because we don't want a lot of entrained solids inside of that type of system.
Vortex flow meters have been around for a long time as well. It's an older technology, very stable and well understood. It uses a bluff body that's inserted in the flow path in order to make vortices and measure the frequency of the vortices. That frequency is then proportional to the flow rate. So as the flow rate increases, the frequency of the vortices changes. You can also get mass flow with this flow meter fairly easily. Some manufacturers will have pressure and temperature measurements built in, so you kind of have a multi-variable meter ready to go. And then if you don't have one of those, if you have an external pressure and temperature measurement, you can usually feed those in as external inputs and have mass flow measurement come out of your Vortex meter. Both inline and insertion models are available, and some can go into very high pressure applications with a packing gland and sort of a retraction mechanism if need be. Pros and cons. So once again, inline or insertion, just as I mentioned before, there's no moving parts in this one, so that's nice, a little less maintenance. The pressure drop is a little lower on this one because there's just a small bluff body that's inserted into the line compared to, say, a differential pressure flow meter or a turbine meter. Those have much higher pressure drops. They have good accuracy and a pretty good range. They don't do very well down at the low end. So if you need measurement down low flow, just make sure that how low you need it is within the good range of operation whenever you get these sized. It does have a little bit higher pressure drop at the higher end of the range. That's because you're shoving more fluid over something that's in the line. And then you do have to support this meter if there's vibration. And if there is a lot of vibration, then we might look at some other technologies that would be available as well, so you don't have to do that. These are very good for steam applications. A lot of them will have steam tables built into the transmitters, so it's a very cost-effective measurement for steam. It can do both liquids and gases effectively, boiler feed water, and things that are high velocity. So it's a very flexible flow meter.
Hey guys, okay, so now we're on a Vortex meter. This is a Vortex, and a few things on the Vortex is just like on the other meters that we're talking about, we have our upstream and downstream. So flow direction on this one is going this way. There is a little arrow on just about most meters that you're going to see. So you want to install it in the direction of the flow. Vortex meter will work in gas applications or liquid applications. So in a liquid application, usually about maybe 10 pipe diameters upstream, 5 pipe diameters downstream would be preferable. For a gas application, we want to extend that a little bit. So you could have 15 to 20 up and maybe 10 to 15 down. Okay, really the more pipe diameters you have to really ensure that good flow profile is going to be preferred. And then vibration could also be something that we really want to watch out for on these meters, because these work by basically measuring some of the movement and vibration inside the pipe as swirls coming through. And so we want to maybe mitigate some vibration if there is excessive vibration on the line, either by maybe an extra mount of some sort. Other than that, man, Vortex meter.
Magnetic flow meters use Faraday's law in order to determine the flow of a liquid in a pipe. So Faraday's law says that the voltage is proportional to the flow. And it's also linear, which makes this a really nice way of measuring flow. So a magnetic field is placed on a section of pipe, which is the flow meter. As a conductive fluid flows across it, then you have a signal that's sensed by two electrodes, and normally these are on the sides of the pipe at the 3 and the 9 o'clock position as the fluid goes over them. You do have to have an electrically conductive fluid in order to use a mag meter. So these are great for water, brine flows, anything that is conductive. What it's not good for are hydrocarbons. You can't use them for that, and you can't use them for gases. These are nice because they don't require a typical straight run. So, for example, with a turbine meter or a vortex meter, you're going to try to have 10 diameters upstream and 5 diameters downstream straight run for those measurements. With a mag meter, it's typically half of that. So if you have an application where you may not be able to have the full 10 and 5 and you have a conductive fluid, then a mag meter might just be the perfect meter for you. Also, there's no pressure drop in this meter, and that's because the electrodes are at the ID on the sides of the flow meter itself, on the sides of the pipe wall. So you can actually look down the center of this meter and you wouldn't see anything because everything is within the ID of the pipe. This is really nice because of pressure drop, and if you happen to have some slurries or things like that that might be caught in a turbine meter, this might be something that would be a better fit for that application. You can also get 20-to-1 turn down, so that's pretty good for a flow meter. And typically the size of the line is the size of the flow meter, so they're very simple. Pros and cons. Pros are really reliable. They've been in use for a very long time. Once again, there's no pressure drop. They can have dirty, corrosive fluids. The nice thing about mag meters is that they have liners. So you can specify the liner based upon your fluid type. And for severe service, they can come with a ceramic liner. So something that's really erosive that might eat away at other fluid technologies. A mag meter might be the best choice simply because of the materials that it can be made of. It doesn't work on oil, hydrocarbons, usually boiler feed water or DI water. All of the conductive particles or elements that would make that water conductive are already purified out. So you really can't use it in every water application. Something that's very pure water or treated well to get all the ions out of it, it's not going to be conductive because it needs those ions in order to make the measurement. It is really good for dirty fluids. So a lot of times you're looking, unlike PD meters or turbine meters where dirty fluids might have a negative impact, really doesn't matter with this meter. So that's one of the pros about this one. You can do clean or sanitary fluids. That's perfectly fine. It has a wide range of whatever kind of fluid that you want to put in it. You can do large and small line sizes, and unlike some other fluid technologies, you can actually have gravity-fed applications in this one and be okay.
All right, guys, so now we're talking about the mag meter. This is the magnetic flow meter, and a couple of installation guidelines on this is going to be your upstream and your downstream pipe diameters. So upstream being flows coming this way, This will be upstream and then downstream this way. So recommended really depends on manufacturer specific on some of them, but like 5 and 3 on some of your magnetic flow meters. I've also heard 10 upstream, 5 downstream is also very common. Depends on installation around valves. A few things to really consider is on a magnetic flow meter, you have a liner inside of the meter. Okay, and that liner has electrodes that are kind of pressed through them. So we need to be really careful in vacuum services so we don't collapse the liner. Also, high heat applications could cause issues. So a couple things on installation. I've actually got one here. I've got one that's not installed, and we can see that we have these rings right here. Okay, some people think these are shipping rings or some kind of packing. They're not. These are what we call grounding rings. Okay. Because of the way the magnetic flow meter works, you have some issues with, you don't really have issues with it, but grounding is very important. So this helps contact the actual surface of the product that's flowing through it, because we have to have a conductive product on a magnetic flow meter. So we want to leave these on, don't take them off. And if you're dealing with a wafer style, this is a wafer style meter here. You also have flange style. So flange is going to be not too hard to understand, but on a wafer style, we want to install these grounding rings on here. I'm not these grounding rings, these centering rings, like this. And then you put them on the other side too. And what this does is this ensures that whenever you mount it and you put your bolts through, that you're basically just lined up in the pipe properly, because you don't want to be off center. So this helps you get it lined up. You can leave them on there, you don't have to take them off. And it just kind of lines you up. And then when you're doing the flange style, you just want to make sure that you get it installed in a way that it's centered on the pipe as best you can. This is for liquid applications. Horizontal mounting is good. Vertical mounting with flow going up is also good, because we have to have a full pipe. Okay, so full pipe is very important.
Ultrasonic flow meters use sound in order to measure the flow rate in a pipe. There's a couple different kinds of ultrasonic measurement that you can use. One is Doppler. It's an older measurement. There is one transducer that's clamped onto the outside of the pipe in this technology, and it uses particulates or bubbles inside the line in order to bounce the signal off and return it back to the transducer. And the time it takes to do that is proportional to the flow. This is represented here. In order to have a Doppler meter, you have to have something in the line to bounce the signal off of. So you can't use it for really clean fluids because there's nothing to bounce the signal off of. So if you think about it, it's kind of like your fish finder. Your Doppler signal is going down, finding fish, and then coming back up so you know where that is. So it's very similar to this. This is really good for like a wastewater application, something with an open channel. Any dirty fluid or anything with a slurry, you can usually use a Doppler meter for. Transit time is another kind of technology for ultrasonic. In this case, we're looking at kind of a rowing across a river. So if you imagine this is your pipe, you have a flow going this way, and we're going to clamp some transducers on the outside. Now, regardless of whether it's clamp on or wetted, means transducers are actually seeing the process, the concept is the same. So each transducer is both a sender and receiver. So as this one sends a signal, it's received by the downstream one, and it'll take a certain amount of time to get there because it's going with the flow. Now, as the signal goes back, it's going to take longer to get back to that first transducer because it's going against the flow. Much like if you were going to go row your boat across a river, it's going to take you less time to get down to your across the to the other side of the bank with the flow than it is against the flow. So this delta T is proportional to the velocity. And we know the size of the pipe because we've inputted that into the meter to get where we're supposed to put the transducers. So as the flow increases, the delta T gets bigger. The time in between the sending and receiving gets bigger. Similarly, if you have no flow, this delta T is going to be 0 because it's going to be exactly the same amount of time to go up and down because there's nothing inhibiting or pushing the signal faster. These transit time meters are the most used today in terms of ultrasonic. They're very flexible, and you can use them on gases or liquids. Also for a wide range of applications, from water, wastewater, custody transfer, flare gas meters are ultrasonic meters normally, and very high temperature, very cold temperature applications. Pros and cons. So the wetted flow meters, so the ones that are actually installed in the pipe that see the flow, see the process, they're very accurate in terms of custody transfer for both gas and liquid. They're normally used. There's no pressure drop. Like I said, they have a very high turn down, and there's very low maintenance because there's no moving parts. We're simply sending sound through the pipe. So it's sort of like a stopwatch. And so in terms of calibration, you don't really have to calibrate time. You would calibrate your 4 to 20 milliamp output to make sure those are okay. And then you can measure whether or not the meter is actually measuring 0 flow if you can block it in. And that will give you an indication of whether or not the meter is still healthy and performing within diagnostic parameters. Sometimes these can be higher in initial cost. So ultrasonic meters are on the higher side, particularly with larger wetted meters or custody transfer applications. However, they have a lower overall cost point because there's really no maintenance to them. They really are not good for thick slurries unless you're going to use a Doppler. Something like that would be fine for a slurry, but transit time really doesn't like to have liquid droplets in a gas meter or gas in a liquid meter. So that's one of the limitations there. Some of the best applications, as I mentioned earlier, flare, that's a really typical application for a transit time ultrasonic meter. Anything that has a very high or low temperature, this is a good candidate for this. Liquids or gases, either one. This is also a good option for steam meter. We talked with Vortex as being a good option for steam. This one will give you a wider range in terms of turn down on steam, and it's also something you might want to consider. Pig lines, multiple fluids. So if you have a batch plant or you're going to run some different kinds of fluids through the same line, ultrasonic meter might be the right thing because it really doesn't care what's going through the line. You don't have to calibrate it for a specific fluid.
All right, guys. So now we're going to talk about ultrasonic clamp-on, specifically flow meters. Ultrasonic clamp-ons are great because you don't have to break the pipe apart to get a flow measurement. They're used a lot of times inside portable and maybe a portable installation if you just need to check your flow and then move on to another pipe you're doing, maybe verifications, flow verifications. So something I want to show you all on this is, of course, we've got some of the same requirements as our other ones. We want to have a full pipe of liquid, okay, for measuring liquids. So I need a full pipe, 10 pipe diameters upstream, 5 down. This is vertical, so my flow's going up. I'll pull the cover off here. So you can see on this flow meter, on this one, my actual transducers are right behind you here. I don't know if you can see them real well, but these are the knobs on them, so I can adjust them. So when you're setting these flow meters up, you're basically setting it up on the transmitter itself, and you're putting in all the pipe information. So you need to know what your pipe wall thickness is. You need to know the fluid that you're flowing through the pipe. This is sound speed dependent, but most of the transmitters, once you tell it the fluid type, it's going to automatically know what sound speed that it's expected to see. So you're going to need to know your pipe wall thickness, your type of material, pretty much all of your piping information. Enter that into the flow meter. Flow meter is then going to give you a spacing amount. Okay, you're going to tell it how many. We call it traverses. So how many traverses are you making? For example, a single traverse would be I'm going straight across the pipe. So whenever I'm setting up my flow meter and I sell a single traverse, I'm going to put a transducer on this side and this side. If I'm telling it a dual traverse, then the beam is going across the pipe and bouncing back, right? Or I can do, pretty much your even numbers will be on the same side of the pipe, which is typically easier. You'll make your decision on that. It's a little bit of trial and error, but basically if you've got a smaller pipe, you can do maybe 2 traverse. When I set them up, I usually start off with a two traverse and then move up from there if I need maybe more averaging or if I don't like the way of my diagnostics. Like that. So you'll do your spacing according to what the meter tells you. You're just going to space them from center transducer to center transducer. There is some gel that you install in the transducers, and that's basically it. Really good, solid measurement. We recommend them for liquid flow applications. Some manufacturers have the gas ones, but I know that there have been, I've personally tested them on liquid applications and they work great. There's also, for different size pipes or different installations, here's another example of an ultrasonic flow meter here. This ultrasonic flow meter is installed on the smaller size line, and basically the same thing. You can see that you have actual hash marks on the spacing, so you can space it directly reading off of what the holder says. All right, guys, so we've talked a little bit about ultrasonics. We've talked about the Clamp On variety. Now I want to get into this is wetted system. This is actually specifically on a flare. So you have wetted that would be on maybe a natural gas pipeline or something like that, or even cryogenics. We do cryogenics with a wetted, but this specific one is for a flare. So what you're looking at here is a flare meter. It has we have a pressure input on it. We also have a temperature input, as well as these are insertable. So on this flare meter, for servicing purposes, these transducers actually need to be pulled out, and then they can be inserted back into the pipe. They have a packing installed on it, and you would just shut the valve when you pull it out and open it, obviously, when you put it in, and secure it. And then typically you would do your testing on it. This specific one has a single pass. A lot of times you'll have dual passes. So when I was talking earlier, I was telling you about your transducer spacing. It's very important. These are all preset spacings, and this is a single traverse. So you can see that I go across the pipe one time. Okay. If I was going to do dual path, I would have a single traverse, and then I would have another one, maybe an X configuration, where it would also be doing the same thing, or it would be down. It would actually be probably further down the pipe a little bit. You would have another set of them. So this is, like I said, an ultrasonic flow meter, and this specific setup would be a flare setup.
Thermal mass meters use thermal properties of a gas in order to measure the flow in a pipe or a duct. So these flow meters are really for gas only, and I would also not recommend them for steam because any kind of liquid droplets can affect the accuracy of these meters. There's a reference RTD that measures the temperature of the gas, and there is a heated element. So the heated element will then be ramped up to keep a certain temperature, and the temperature between the reference element and the heated is proportional to the mass flow. So one nice thing about this meter is that you can directly measure mass flow in a gas. Very, very cost effective for fuel gas, airflow, any kind of gas that's not really going to change composition all that much. Or if you need a high turn down. this is another meter that will give you a really high turn down. This one is anywhere from 100 to 1 to 1,000 to 1. It also has a very, very fast response to it, and can be found in either insertion or spool piece inline meters as well. Pros and cons. As you can see, there's a couple of them pictured on this screen. The top one is an insertion meter, and you can kind of see what it would look like going down through a weldolette or something like that in order to insert it into the line. It's usually inserted roughly halfway or in the top third of the line in order to get a good measurement. And then the bottom picture is an inline meter. Normally we see these for smaller pipes because if you use them in larger pipes, then it's simply going to be more expensive because you're buying the pipe itself. Pros, these have very rapid response, virtually no pressure drop. The amount of insertion into that line is significantly smaller than, say, a turbine meter or even a vortex meter. So they're going to have lower pressure drop for you. There's no moving parts here either. So like a mag meter, like ultrasonic, lower maintenance costs because nothing is moving inside the line. These measure low flow really well, and you can use them in very, very large pipes by simply using an insertion meter. You do have to calibrate this for a given composition. Some manufacturers will allow you to input a specific composition in the field and then kind of get your gas mix up to date that way. In case you have a gas mix that slightly changes, you can change that in the field without having to send it off for calibration. And then other manufacturers will also be able to give you kind of a plus or minus range of if you stray from the calibrated composition, what would your error be? So that way you at least know what it would be. Droplets can affect accuracy. So anything that you're having liquid droplets, it will cool the thermistors in there and give you an inaccurate reading. Really good for low pressure gas, stacked gas, natural gas, any kind of pure gas. You can use them in some flare applications, mainly for some upstream type applications. Nothing that you would think of widely varying compositions because you have to stay kind of close to your composition here.
Okay. So guys, what we have here is a thermal mass meter. This is going to be a gas meter for gas flow. The one that we're looking at here is actually an insertion style meter. Okay, so this is inserted into the pipe. On these, we want to have about 10 pipe diameters, 15 pipe diameters upstream, and then 10 pipe diameters downstream. They're also available in a spool piece style. And on the inline, you could do 8 diameters up and 4 pipe diameters down. So a few points on this. On this particular one I have here, my flow direction is pointed out by this little thing here. Okay, this is pointing which direction it needs to flow. That is important. These are insertion styles, so something I might bring up on this is going to be kind of the safety whenever you're inserting and uninserting the pipe. There is pressure on this, so when I break this, you want to make sure that you're really kind of pulling on this and be aware of what your pressure is in your line, because this could really force up with some pressure. You can see there's a safety wire here that keeps this from basically launching off like a missile. So I have seen guys kind of forget about that. They break this nut here to uninsert it, and I mean it comes up with some good force. So keep some pressure on it. Then once it's up, you can close your ball valve and you can pull the meter out. These are great flow meters. They work based off of some temperature. I know Shannon was just telling you how they work. They're really good flow meters. We do need to have moisture to be a consideration. We don't want excessive moisture in the line. So it needs to be installed into place to kind of mitigate that moisture buildup where it doesn't kind of build up here on the bottom of the line.
Coriolis meters They use a vibrating tube, which when fluid goes through it, it causes kind of a deformation or a change in frequency, a phase shift that can be measured. And that is proportional to the amount of mass that's going through it. So ultrasonic is a volumetric flow meter. Turbine meters, those are all volumetric flow meters, but kind of like a thermal mass meter, this gives you mass flow directly, which is nice. It can also tell you the density of the fluid or gas that you're passing through it. It can give you a temperature, concentration, and these have also been used for net oil and water cut meters as well. The effect, I like to think of it if you're holding a water hose that's attached to a faucet and it's empty, but you have kind of a slack in it, a little loop in it, and you're holding it almost like you're waiting to have a jump rope. Once you turn the water on, that water hose is going to deflect a little bit. That's the Coriolis principle. And when we control the amount of vibration that happens with no flow, when there's flow that goes through that, we can measure that deflection, and that is proportional to the mass flow. So where can these be used? Really, any liquid or gas, you can use these in sanitary applications. You can use these where you need really high accuracy as well. Sometimes the Coriolis meter is the best meter for allocation or custody transfer, depending on what you're looking for. They're very reliable, and they'll give you a density measurement. They also need no straight run. As you can see in the picture, there's not a whole lot of straight run. Pretty much just enough to put the meter in and you're good to go. The cost is going to be significantly higher, particularly for greater than a 4-inch meter than some other technologies. So just keep that in mind. And you're going to have a larger pressure drop in this meter than you would in others, simply because it's going through kind of a U-shaped tube in order to make the measurement. There are some manufacturers that have tubes that are straight. There still will be a pressure drop in there because usually the tube inside the meter is not the same as the line that you're flanging it to. So there will be a pressure drop regardless of whether it's a straight tube or a bent tube meter.
All right, guys, so a Coriolis flow meter. So we're going to talk about Coriolis. Coriolis is actually our mass flow meter, meaning pretty much everything else I talked about really concentrates on volume, whereas your mass flow, which is the Coriolis, is actually measuring mass. So some unique things about the installation on these. The one that we're looking at right here, this is actually a remote. So you can see I have a flow tube here with a transmitter over here. But what's unique about it is I don't have straight run requirements, okay? So that's kind of nice. Now, if it's possible, I'm always going to recommend, even though the manufacturer states, hey, yeah, we don't need straight run requirements, just call it personal preference. But if I have a choice, I prefer some straight run. But if not, you can mount it straight up to the end of a pipe. So some things to, or I guess a bend or an elbow. Some things to keep in mind on these is you don't want a whole lot of stress on the pipe, okay? Because you do have some tubes that float inside that need to be able to move and bend. So try to keep your from flange to flange. Your mounting needs to be straight. Other than that, great flow meter. For as far as mounting goes, this can be for a liquid application. It's going to be tubes down, so you'll do tubes down for liquids. For gas applications, you'll actually flip these tubes up, okay? And the reason that being is we don't want the any liquids that can condense in the lines. We want those to flip to the bottom. And same being said about liquids. So with it being mounted tube down, you basically have a P-trap down here, and we want the any air bubbles to flip to the top that might be in there. So we don't want a lot of gas entrained. It's either a liquid measurement or it's a gas measurement, but no multi-phase. Vertical mounts. You can mount vertical. That's a very preferred method for both liquids and for gases. You want flow to be going up. There is an arrow on the meter, on the flow body, telling you the flow direction.
Thank you for your time. If you have any questions, please let me know.